quite sure.
Just the second class.
I understand. So from the educator's perspective, now let me ask you as the educator, when was the last time that you asked your students how interactive and how engaging the school experience is for them, and actually took their ideas and them to make school a better experience for everyone? I've seen on Facebook and on Twitter how students will text every day and talk about how boring school is and how they'd rather be elsewhere, and never mind, they text all this while they are at school. Studies have been done and conducted that suggest that teachers are now not only competing with the lunch siren for the students' attention, it's technology that you have to take into account. We know that our learners learn through doing most of the time. So technological means, if I give you now today this lab to take home, by the end of the week you probably won't know how to use it. But if I give you an iPad, by the end of the week you'll know every button that is on the iPad itself. So now new and innovative approaches to learning have to be introduced that merge the practical application as well as the theoretical approach to create for a broader understanding and a more interesting environment to be in. This is why today we bring to you the Parrot Interactive Whiteboard and the Chembiz Mobile Lab. The Parrot Interactive Whiteboard is made up of the Parrot software, which is a desktop software that can be installed onto your computer that lets you prepare well-detailed presentations for your class, and also gives you the ability to do on-screen editing while you are in class for you to add that extra bit of information that you might forget to put into your presentation. At the same time, it also allows you to do things like your annotation, highlighting of key information, handwriting recognition, which changes your handwriting on the screen into typed text, and the recording and playing of video and audio clips for your classroom. The Chembiz Mobile Lab Station, as the name would suggest, is a mobile lab station that you can transport into any classroom situation. It would be best used in a situation where a school does not itself have a chemistry laboratory on the premises. Then it allows for hands-on applications whereby the students can now come and try out the ideas that have been presented by the educator. So now instead of just sitting down and copying down everything, they can come and practically do it on the board itself. It comes with a range of physics and chemistry experiments that cover a range of topics from motion, electricity, to redox titrations, amongst many others, as we'll be displaying to you today. So for today, my topic for presenting will be the G-force, which is the calculation of the gravitational acceleration of objects in free fall. And Mr. Beggy will be presenting the standardization reaction between sodium hydroxide and hydrochloric acid. So now, what is gravity? To define gravity, gravity is the mysterious force with which all objects are attracted towards the center of the earth. It is, in layman terms, a force that makes everything to fall. Mathematically, the gravity was first defined by Sir Isaac Newton, whose ideas were later worked upon by Sir Isaac Newton and others to create a wide range of topics, including relativity. It is said that all objects in the universe attract each other with a force, with a specific force which is called gravity. Now, different sized objects will exert this force in different quantities relative to their sizes. Is gravity important? According to you guys, do you guys think gravity is important?
Yeah.
What are the implications of not having gravity? To mention but a few, without the Earth's gravity, objects will just float about randomly. You kick a soccer ball and it will fly endlessly and never get to the goal. Admittedly, the ball floating would be fun the first few times, but it destroys the whole point. Now, without the sun's gravitational pull, the Earth itself would fly out of its orbit. You know that the sun attracts the Earth with a certain force which keeps it within the orbit. When it flies off the orbit, life can no longer be sustained. We'll either go too close to the sun and burn, or we'll go too far off and probably freeze. Then let me explain the concept of free fall. When we say a body is in free fall, it's when it's defined as the motion of a body whereby gravity is the only force that's acting upon your object. All objects in free fall will drop towards the earth at the same speed. This is called the equivalence principle, and this speed is known as the gravitational acceleration. This means regardless of the size, if any two bodies are dropped from the top of a building, they should theoretically drop to the ground at the exact same time because they're accelerating at the same speed. This gravitational speed on Earth was determined through calculations to be approximately 9.8 meters per second. Now, to calculate your force of gravity, you need to take into account the equation that says the change in your height is given by your initial velocity plus half of gravity times the change in time, which is the time taken for the object to move from its initial position towards the ground. Now, when the height above the ground is known and the time taken for the object to fall is also known, the only unknown in my equation now will be gravity, because I know that the initial velocity is 0. Can I just see why am I saying the initial velocity is 0?
It's from rest. Starting from rest.
Exactly. Because your object is dropped from point of rest, the initial velocity that it's moving with will be 0, and then it will fall down towards the ground. So now with this 0, if I have the 0 and I know the change in height and I know how long it takes for it to fall to the ground, I'm only calculating my g, which is the gravitational acceleration. For example, if I was to say calculate the gravitational acceleration of a body in free fall from the roof of a 10-meter high building, if it takes the body 2.04 seconds to reach the ground. Now, according to my equation, where now my change in y will be the height of the building, which is 10 meters, the initial velocity, as we said, is 0. The gravitational force, the gravitational acceleration, is what we are calculating, and your change in time is given as 2.04 seconds. Making g the subject of the formula leads you to the conclusion that your gravitational acceleration is indeed 9.8 meters per second. Now, we are going to practically calculate the force of gravity through the means of the free fall apparatus. We've already assembled the apparatus, and it's set up of the retort stand, the rod clamp, release mechanism, shock plate, a ruler, and the timer. So the principle behind this is a ball is magnetized onto the top of the plate, and when you demagnetize it, the ball should drop to the ground. The timer captures the time that it takes for the ball to drop from the initial position to the final position. So in doing this now, we know that the ball is not moving. My initial velocity is 0, right? So now, when I demagnetize my ball and it falls, I get a reading on my timer. So you're gonna repeat this 3 times so that we all can calculate the average value.
So then where do I see the time for that here?
Yes, that's
Okay, so 0.241 seconds.
Yeah, then I just printed to
Yeah.
the camera.
0.241.
you can show it to the camera.
I'm not showing to the camera. Okay.
So that we trust you.
Magnetize
Magnetic skills. That's the problem.
And it takes
0.241 seconds. Oh, the reset. Right. What is it? Okay, we do it again.
And the plate.
take
Magnet to the bottom as well. Okay, cool. And let's do the. Okay. 0.315 seconds.
We want to see, we can't see the time.
Okay. Does it show there as well?
Yes.
That is so cool. I have to reach out. You see? Yeah.
So you say your first time value now will be the 0.315.
Yeah.
Okay. Reset. Magnetize.
Let's see. Okay, here we go.
And release.
And
So
show it again to the camera.
Yes.
Can you all see?
0.315.
Okay. Can you all see?
0.314. So now with the 3 times that you have just calculated, sum them up, divide them by 3 so that you get the average time that the ball takes to reach the ground.
50 centimeter height.
That equals to
Everyone looks very confused.
and then I got this. And I got this.
Did you times this by 2? Divide this by 2?
You use it.
I guess we can cancel out half.
How much did you get for your change in times?
No, it's still
0.29.
0.29.
Mm.
How many of the values did you use?
3.
3. Which
Oh,
one?
which values did you use?
0.241, which is wrong. 0.
Which is wrong?
Which is wrong?
0.315,
Please don't cut him off.
0.314, of which the average should be approximately 0.315.
Yeah, you see, you give me wrong values.
I didn't remember them.
So imagine it in the bag across now.
We said how much is your initial velocity?
5.
It's 3?
1.5.
1.5.
Yeah.
Okay. So now for your calculation now, we want to make G the subject of the formula where G is our unknown, right? So to calculate for G now, we're going to use the formula. I'm gonna use the formula change in Y is equal to VI plus 1 over 2 G delta T. And knowing the values of my first, how should the value of the height be written? In meters. So converting 50 centimeters to meters gives you 0.5.
What are you guys doing? I think it's
So 0.5 meters will be equal to the 0 plus 1 over 2 G times your change in time, which is your 0.315. So the value for G now will be given by 0.5 times 2 divided by 0.315, which gives a value of
7.4 something. Yeah, that's why we were all like, what's
you getting?
317.
How are you getting?
We put it exactly.
3.174.
The exact one.
3.17.
3.17. That's what I'm
Not
getting
quite.
as well.
Yeah.
Which is really far off from what we want.
But why did you
Let's
get
do
that?
it.
Why?
Yeah.
Let's do this. Let me first confirm my height to be sure that we're doing the right thing. So it's from 1 centimeter.
Right. So, okay, let's move on. Right. Special names for some everyday quantities. You know this. You guys, you talk about 1 gig, which is what? There you go. Those are special names for special quantities. Now I'll give you a couple of them here, and I would want you guys to play around because I just put them in a different order. Let's see if it's going to allow me. There you go. Right. Can somebody come over here and point to the correct special quantity? Because they're mixed up now.
Yeah.
Right.
We got this one.
Choose a color, choose a color, choose a color.
Favorite color? I'll take that.
Right?
You don't say.
All right.
Where's the trick? That's why.
I don't think you have that.
Okay, thank you. Thank you. Next one. Yes. There you go. 10. Okay. What else? Yeah, I think that's it. That's it. Thank you very much. So these are special names for special quantities, right? We're used to this, right? Now in chemistry, we have got such a special quantity as well, which we give the special name. Now, here's the reveal. The special quantity. 12 grams of carbon-12 isotope, we call that a mole. The number of entities in 12 grams of carbon-12 is called a mole. Are we together? Right. Right, so it's the same thing. So you need to calculate the molarity when you're doing solutions. And there is the mole there. Right. Okay. Right, look at me here. I've got my standard in there. I'll then measure the volume, right? Once I've measured the volume, that reacts completely. My analyte will be here, or my unknown will be here. So I put there, I react these two, then I measure the volume. Now, that method is called volumetric titrimetric, simple titration. So how does the mole comes into the picture now? We need to determine the number of moles of the standard. That will react with the number of moles for the unknown. That is how the mole concept comes in. You understand that? Okay. Because in chemistry, it is very, very important that we know, we quantify things. It's very, very important. We need to quantify. We need to know how much of that is in that, how much of that is related with that. That is very important, right? And what are the products? Suppose it's a chemical reaction, right? What are the products? How much of the products? That is also always a very, very important point. Can you take your water bottles there? Have a look at the other side. Nutritional information. Can you see their values there? Because we want to know. We want to know what is in our water, isn't it? And that's the job of analytical chemists. They have to tell people that there's so much of calcium, so much of magnesium, so much of this and that, all right? All of that, you can do it using titrimetric or titration, for instance. Right, so very, very important concept. Right, let's move on. There are two types of volumetric titrimetry or titration. There is what is called volume to volume, which means the standard is in a solution form and the unknown is in a solution form. Like the setup I have here, it's a solution in there. I'll also put a solution in there. So you call that volume to volume. Good. Yeah, with me. Okay. Right. Here's another one, the second one. There is a mass to volume titration. In which case now, I take my standard. It will be in the form of a salt, which I don't have. Supposing this is the salt, right? I take this salt, go to a weighing balance, weigh a certain amount, and then dissolve it, right? And put it under there. That will be my standard. Then my unknown will be in here. Then I react the two. Can you see how the mass thing comes into the play now? I started off with a certain mass, right? Which I dissolved, and then I react the two together. All right? Yeah, please.
Sugar.
As I said, I'm not a science person. I love tea.
So there you go, I've got sugar here, which is our salt, our solute, right? So if I take a certain amount, measure it in a weight balance, then put it in a conical flask, I dissolve that with a certain amount of water, right? And then I react it with a standard from a burette. With an unknown from a burette. Then that is a mass volume titration. Together? Okay. Let me see how far I can stretch it.
Can I just
50 mils or 100 mils to dissolve that. Does it make any difference in the number of moles in there? What do you think? Think hard. Does it make any difference? I've weighed a certain amount, put it in a conical flask, added my solvent, right? Then dissolve. Does it matter if I put 100 mils or 50 mils of water? Yes, sir.
I don't think the number of moles is affected. I think just the concentration. Because at the time it created or destroyed, so it will remain constant.
So the moles, can you imagine, take marbles, you know marbles? I take 10 of them, put it in a conical flask. If I add 100 liters of water or 200 liters of water, does the number change? No. It doesn't change. All right, keep that in mind. All right, let's move on. Now, in a titration, we are reacting two substances, the standard and the unknown. When these two substances have completely reacted with each other, no excess of the other, we say we have reached what is called an equivalence point. There it is there, equivalence point. It's a theoretical one, meaning that it's not really practical, but we can estimate its position by the changes that would have happened or occurred in here. If it's an acid and a base, for instance, I'm rating those two. It's a neutralization reaction, all right? So I'm starting off with a base in there. The pH will be in the alkaline range, isn't it? Am I right? Right? Then I'm slowly adding an acid. What do you think will happen to the pH? It will drop until towards the acidic side, isn't it? Now, we can estimate that equivalence point by using a very good agent, FBI agent. That FBI agent is the indicator. Now, the indicator changes with the physical conditions inside the conical flask. So this indicator can tell us that, look, we've moved from the alkaline to the acidic side by changing color. We are together there, yes. Yes. So that's the FBI agent there. So it will tell us what's going here. Right. Then take this indicator. Before I take the indicator, can you see the base and the acid there? Right, let me do that. Right, which is which?
sodium
hydroxide.
Is that one there? Okay, so we go this way. So let me do this. Just a little bit. That's enough. And here. And let's see if these two guys or this phenolphthalein indicator can tell us what's happening there. Right? See that?
Yeah.
In sodium hydroxide, sorry, in an acid, it didn't change color. But in sodium hydroxide, it changed color. That's the purpose of the indicator, right? So therefore, we can use it in a titration experiment. So there you go. Now, here is the important part. We want to tie everything together now, the mole concept. Once we have the moles, we can use the molar mass of any particular substance to get the mass of that substance. Together? Are we together? Or we can use the moles, use the Avogadro's number, and then you can get the number of molecules. So this is a very nice schematic thing that can actually help you move either towards calculating the number of molecules or towards calculating the mass. Very, very useful skill. Now, maybe this one you need to scribble it somewhere in your notebook. Because you will have to use this. Right. Molar mass and moles, right? So what does this mean? You weigh a certain substance, right? You know the molar mass because you know what substance it is. Then if you divide mass by molar mass, you get moles, right? Or you can use it either way. Here, this line, the vertical one, you multiply, the horizontal one, you divide. So it's a very useful way of trying to memorize the relationship between mass, molar mass, and that. Now let's move on to the other one, which is this side now. You can measure the volume, right? Together with molarity, you multiply these two, you get your moles. So it is a very, very useful schematic way of trying to remember how to play around with the relation between moles, volume, and molarity. All right. In this case, water. Keep that equation in mind as I explain this one. Starting with the moles, starting with the moles, okay, this side is the standard, all right? You measure the mass of the standard, then you multiply it with the molar mass, then you get the moles of that particular substance. Now, once you have got the moles of this substance, you then use the coefficients of, or what the coefficients that you find in this reaction. What is a coefficient? This 2 is a coefficient there. 1, we know there's 1 there, but we don't normally write it, okay? So those are the coefficients that I'm talking about. So you use the coefficients from the equation, then you can come up with the moles of B and use the molar mass, eventually you can get the mass of substance B. So you can now calculate the unknown. It's another way of trying to simplify the relationships that exist when you're dealing with molar mass, mass, moles, and so on and so on, okay? All right. This one here is just the repetition of the same thing, right? It's just a repetition there. All right, now let's summarize. We talked about the mole concept. We now know what a mole is. We have seen how it is applied, particularly in chemistry, analytical chemistry, in solutions chemistry, in titrations, and when we talk about titration, we talk about the equivalence point. We also talked about indicators, which is a very good friend, particularly when you're doing titrations, all right? And then the interconversions. So what those schematic diagrams that I've been showing you are just interconversions between the different factors that or the relationships that the mole has. Right, now we are slowly inching towards our practical, right? We now know what the mole is. Now, let's talk about this. Volumetric glassware. Ladies and gentlemen, not all glassware is used to measure volume. There is some misconception somewhere that you can take a measuring cylinder or take a beaker, it's written 200 here, and then you say, no, this is not accurate, right? 3 types of glassware which are important in analytical chemistry is a pipette. It has been graduated specifically to measure volume. And if you look at it, they will tell you that it has been graduated to 25 mils. And they will give you some bit of a tolerance, some error, plus or minus 0.03. It has been specifically calibrated to measure exactly 25 mils. So you cannot measure using this 25 mils. No, this is the best. Then that is followed by a burette, which is what you see here. Again, it has been graduated, calibrated to measure volume. The other one is the volumetric flask. So these 3 in a chemistry lab, that's what you use to measure volume. We are together there now. Now let's go. I want Avogadro's number here. So can you write quietly for the 2? This is A. This is B. I want the answers for those 2.
So you want Avogadro's number for
Both of them. 1 mole water, 1 mole CO2. You write that. You write.
You didn't hand it in.
Right.
Don't doubt yourself.
So,
Don't what?
so these guys are the 2 of you and here are correct. Right, guys, let's start. Let's start. Let's start. Let's start. Let's start.
which side opens here? Yes, 1, exactly 1. Isn't it too little?
No?
Okay.
It's not ready with anyone else. It's ready with access. Right.
Please also me, I need Mr. Manyama saying saving my reputation. So, I don't know the guys.
Yeah. Just water, deionized water. Alright, that's a question for you. I did ask you that question. Does it change the number of marbles that are already in there?
No.
Good. So it doesn't affect me. Concentration.
Kids not doing that, getting us excited.
I don't know the concentration, so I don't want to take any unnecessary risk.
Okay, that's good.
I don't know the
For you guys, I think the 3 volunteers, we may have to take them in the department.
That's issue. You said you didn't.
Take them next year.
So what if we want to
Throw pass. They're brave enough, isn't it? We want brave scientists. Because
so brave.
on the tap, right? And instead of going horizontal,